Welcome to Cosmic Whispers, where cosmic mysteries come alive. Your journey beyond the stars begins now. In the vast expanse of our Milky Way galaxy, Earth circles a solitary star, our Sun. But across the cosmos, binary star systems are far from unusual. In fact, more than half of all star systems in our galaxy consist of two or more stars orbiting a common center of mass. This astronomical arrangement raises a fascinating question. What would happen if Earth had two suns? To understand this hypothetical scenario, we must first examine the nature of binary star systems themselves. These stellar partnerships come in several varieties, each with distinct characteristics that would dramatically alter Earth's environment and the evolution of life as we know it. The most common type is the wide binary, where two stars orbit each other at distances hundreds or even thousands of times greater than the Earth-Sun separation. At the other extreme are contact binaries, where two stars are so close they actually share their outer atmospheric layers. Between these extremes lie detached binaries and semi-detached binaries, where one star may be pulling material from its companion. In our thought experiment, the specific type of binary system Earth might inhabit would determine almost everything about our planet's environment. Every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning, and your support means everything. If you enjoy unraveling the mysteries of the universe, hit subscribe. It's free, and it helps us grow this community together. For the sake of our exploration, let's consider the most stable arrangement: Earth orbiting one star of a wide binary pair with a second sun located much farther away. Astronomers call this a hierarchical system, and it represents our best chance for a habitable two-sun Earth scenario. Our current sun, a G-type main sequence star we'll continue to call the Sun, would remain Earth's primary. The second star, let's say an orange K-type star somewhat smaller than our Sun, would orbit at a distance of perhaps 50 astronomical units. For reference, 1 astronomical unit, or AU, equals the Earth-Sun distance, approximately 93 million miles or 150 million kilometers. At this distance, our second sun would appear as an extremely bright star in Earth's sky, hundreds of times brighter than Venus at its most brilliant, yet still 10,000 times dimmer than our primary sun. It would cast noticeable shadows during Earth's night and would significantly reduce the darkness of our nocturnal world. The orbital period of such a wide binary might be several hundred Earth years, creating long gradual cycles of brightening and dimming as the second sun moved closer to and farther from our solar system's inner regions. This astronomical arrangement would completely redefine Earth's climate patterns. The energy budget, the balance of incoming and outgoing radiation that determines Earth's temperature, would fluctuate in complex ways as the second sun moved through its long orbit. During closest approach, when both stars illuminated the same hemisphere of Earth, surface temperatures would rise significantly. When the stars illuminated opposite hemispheres, night would never fully fall on Earth. Instead, we would experience a perpetual twilight as one sun set and the other rose. These changing patterns of illumination and heat would create climate cycles unlike anything in Earth's actual history. Seasons would become more complex, dependent not just on Earth's axial tilt and orbital position around our primary sun, but also on the position of the second sun in its centuries-long orbit. In our two-sun scenario, Earth's climate would undergo profound transformations. The most immediate and obvious effect would be an increase in the total solar radiation, or insolation, reaching our planet. With the second star adding its energy to our environment, Earth would receive significantly more heat and light than it does in reality. How much more? That depends on the second sun's characteristics. If we consider a K-type star with about 70% of our sun's mass, it would contribute roughly 20 to 40% additional energy during its closest approach. This extra radiation would push Earth well beyond the conventional habitable zone, the region around a star where temperatures permit liquid water to exist on a planet's surface. To maintain habitability in this two-sun scenario, Earth would need to orbit farther from its primary sun than it does now, perhaps at 1.2 AU instead of 1. This greater distance would compensate for the additional heat from the second sun, maintaining average global temperatures within a livable range. Even with this adjustment, Earth's climate would experience dramatic oscillations over time. As the second sun moved through its orbit, approaching, passing by, and then receding over centuries, Earth would cycle between periods of relative warmth and coolness. These grand cycles would be superimposed on the seasonal patterns caused by Earth's axial tilt. Imagine Northern Hemisphere summer coinciding with the second sun's closest approach. Regions already experiencing warmth would receive additional heating, potentially pushing temperatures to extremes. Conversely, during winter in the same hemisphere with the second sun at its most distant, the cooling effect could be more pronounced than what we experience today. These variations would create massive challenges for Earth's ecosystems. Plants and animals would need to evolve strategies to cope with these long-term climate oscillations. Some species might develop dormancy periods to survive the hottest epochs, similar to how certain organisms hibernate during cold seasons in our single-sun world. The hydrological cycle, the movement of water between Earth's surface and atmosphere, would also undergo significant changes. Greater insolation would increase evaporation rates from oceans and lakes. This would likely result in a more active water cycle, with higher precipitation globally, but distributed unevenly. Some regions might experience intensified monsoon seasons or more frequent extreme rainfall events. Others could suffer prolonged droughts as weather patterns shifted in response to the changing energy inputs from the two suns. Ocean currents, which play a crucial role in distributing heat around our planet, would reconfigure to accommodate the new thermal gradients. The thermohaline circulation, the global conveyor belt of deep ocean currents driven by temperature and salinity differences, might follow dramatically different patterns than in our single-sun Earth. Perhaps most striking would be the impact on Earth's polar regions. The additional warmth from a second sun could prevent the formation of stable ice caps, particularly during periods when the second sun was at its closest approach. Without these white reflective surfaces to bounce solar radiation back to space, Earth would absorb even more heat, creating a feedback loop that further warmed the planet. The relationship between Earth's axial tilt and its orbit around the primary sun gives us our familiar four seasons, but in a binary system, this relationship becomes far more complex. The gravitational influence of the second sun would likely cause Earth's axial tilt to vary more dramatically over time, potentially creating radical seasonal shifts that would make our current climate variations seem mild by comparison. The gravitational dance of a two-sun Earth system introduces complexities that go far beyond climate effects. In astrophysics, the three-body problem represents one of the most challenging scenarios to model mathematically. Three objects, each exerting gravitational pull on the others, create motion patterns that can become chaotic and unpredictable over time. In our hypothetical system, Earth, the primary sun, and the second sun would constitute such a three-body system. The stability of Earth's orbit, something we take for granted in our actual solar system, would become much more precarious. For Earth to maintain a stable orbit in a binary star system, certain conditions must be met. The most viable arrangement would be what astronomers call an S-type orbit, where Earth circles just one of the stars at a relatively close distance, while the second star orbits much farther away. The alternative, a P-type orbit where Earth circles both stars, would likely place our planet far beyond the habitable zone, resulting in a frozen world. Even in the more favorable S-type scenario, Earth's orbit would experience perturbations, subtle shifts and wobbles caused by the gravitational pull of the second sun. These perturbations would accumulate over time, potentially causing significant changes to Earth's orbital eccentricity, how circular or elliptical the orbit is, and inclination, the tilt of the orbital plane. In the worst case, these gravitational disturbances could eventually eject Earth from the system entirely or cause it to collide with one of the stars. More likely, Earth would settle into a quasi-stable orbit that varied considerably more than our current nearly circular path around the Sun. This orbital variability would have profound implications for Earth's climate beyond the direct effects of the second sun's radiation. As Earth's orbit became more elliptical, our planet would experience greater extremes in solar heating throughout the year. During closest approach to the primary sun, perihelion, temperatures would soar. At the farthest point, aphelion, they would plummet. The second sun's gravitational influence would also affect Earth's axial precession, the slow circular motion of Earth's axis that currently completes one cycle every 26,000 years. In a binary system, this precession would likely occur much faster and with greater variation, triggering more frequent and dramatic shifts in seasonal patterns. Perhaps most significantly, the gravitational interactions between the two suns could affect the second sun's own orbit over time. In some scenarios, this could result in the second sun periodically approaching much closer to the inner solar system than its average distance. These close passages would create hot epochs lasting decades or centuries, potentially triggering mass extinction events on Earth. The Moon, Earth's faithful companion, would also be caught in this gravitational complexity. The Moon stabilizes Earth's axial tilt, preventing the wild variations that would make our climate even more erratic. In a binary star system, the Moon's orbit around Earth would be subjected to additional gravitational perturbations, potentially destabilizing this arrangement. If the Moon were pulled into a more eccentric orbit or even ejected from the Earth-Sun system, our planet would lose this stabilizing influence. The axial tilt could then vary dramatically, perhaps swinging from 0 degrees, no tilt at all, to 90 degrees, completely on its side like Uranus. Such extreme variations would create seasonal changes beyond anything in Earth's evolutionary experience. These orbital and rotational complexities would have cascading effects throughout Earth's systems, from atmospheric circulation patterns to ocean currents, from magnetic field generation to the length of days and years. Life would need to evolve remarkable adaptability to survive in such a variable environment. Life on a two-sun Earth would face evolutionary pressures unlike anything in our planet's actual history. The organisms inhabiting such a world would need adaptations far beyond those seen in terrestrial species, responding to challenges ranging from complex light cycles to long-term climate oscillations. Let's begin with plants, the foundation of most terrestrial ecosystems. Photosynthesis, the process by which plants convert light energy into chemical energy, has evolved for a single sun world with predictable daily and seasonal light patterns. In a binary system, plants would need photosynthetic mechanisms capable of efficiently utilizing varying light intensities and spectra as the two suns move through their relative positions. If our second sun were a K-type star, it would emit light with a different spectral composition than our G-type sun, more orange-red and less blue-violet. Plants might evolve multiple types of chlorophyll or other photosynthetic pigments to capture energy across this broader spectrum of available light. The inconsistent day-night cycle would also require significant adaptations. Many plants use photoperiodism, the physiological response to day length, to time critical life events like flowering, germination, and leaf drop. In a two-sun world with periods of constant twilight, plants would need alternative timing mechanisms or the ability to respond to more subtle light cues. For animals, the irregular cycles of light and dark would disrupt circadian rhythms, the internal biological clocks that govern sleep, feeding, and reproductive behaviors. Species might evolve split sleep patterns or the ability to opportunistically rest when conditions permitted, rather than following strict diurnal or nocturnal schedules. Visual systems would need to accommodate dramatic variations in ambient light. Animals might develop eyes with adjustable sensitivity far beyond what Earth creatures possess, perhaps with multiple types of photoreceptors optimized for different lighting conditions. Alternatively, some species might evolve to rely more heavily on non-visual senses like echolocation, electroreception, or chemical detection. The long-term climate oscillations caused by the second sun's orbital cycle would present another significant challenge. Species would need mechanisms to survive or adapt to centuries-long warming and cooling trends. This might include complex migration patterns spanning generations, or physiological adaptations like specialized hibernation or estivation behaviors triggered by environmental cues. In our actual evolutionary history, Major climate shifts, typically, occurred over thousands or millions of years, allowing gradual adaptation through natural selection. The relatively rapid climate oscillations of a binary system might favor species with high genetic variability and shorter generation times, capable of evolving more quickly in response to changing conditions. Some organisms might evolve synchronization, with the long orbital period of the second sun, timing major life history events like reproduction or metamorphosis to coincide with specific phases of the cycle, perhaps reproducing more during moderate periods and entering dormancy during extremes. The oceans, covering more than 70% of Earth's surface, would experience their own disruptions. Marine organisms rely on predictable patterns of light penetration, temperature gradients, and current flows. In a two-sun world, these factors would fluctuate in complex ways, potentially leading to more frequent algal blooms, migrations of marine populations, and restructuring of food webs. Intelligence itself might evolve differently under these conditions. The premium placed on predicting and adapting to complex environmental patterns might favor the development of advanced cognitive abilities. Species capable of observing astronomical cycles and preparing accordingly would have significant survival advantages. Perhaps most fascinating would be the cultural and perceptual adaptations of any intelligent species evolving on such a world. Their scientific understanding, mythologies, art, and architecture would all reflect the presence of two suns and the complex patterns they create. Their concept of time might naturally incorporate both short-term solar days and the grand cycles of the binary orbit. On a two-sun Earth, the fundamental rhythm of day and night, the most basic cycle governing life on our planet, would be dramatically transformed. Depending on the positions of both stars, Earth would experience a variety of illumination patterns, unlike anything in our familiar world. When both suns appeared in the sky simultaneously, daylight would be significantly brighter than what we experience. Although our second sun would contribute only a fraction of our primary sun's light, the combined illumination could be up to 40% more intense during periods of closest approach. This increased brightness would require biological adaptations for eye protection and heat regulation in diurnal animals. More intriguing are the periods when the two stars appeared in opposite hemispheres of Earth's sky. As our primary sun set in the west, the second sun might be rising in the east, creating a twilight unlike any on our single sun Earth. Instead of the relatively brief transitional period we experience between day and night, this twilight could last for hours, creating a third distinct phase in the daily cycle. During certain alignments, Earth might experience what could be called a double day, a period of primary daylight, followed by twilight as the main sun set and the second sun rose, then a second dimmer day illuminated solely by the secondary star, before finally transitioning to true night as the second sun also set. The color of light would change dramatically throughout these cycles. Our primary sun's light appears white to yellow from Earth's surface, but a K-type second sun would cast distinctly orange-amber light. During their combined appearance, these different wavelengths would mix, creating unique lighting conditions that would affect everything from plant growth to animal behavior to how the human eye would perceive color. Let's consider what the sky itself would look like. During primary daylight, our second sun would likely remain visible as an extremely bright star, far brighter than Venus appears in our actual sky, easily visible even during full daylight. During the twilight phase, with both stars above the horizon, fascinating optical effects might occur as light from both sources scattered through Earth's atmosphere, creating complex and beautiful patterns of color. Shadows would tell their own story in this two-sun world. With two light sources in the sky, objects would cast double shadows of varying intensities. As the relative positions of the stars changed, these shadow patterns would shift throughout the day in ways that might seem almost animated to observers. The night sky would appear dramatically different as well. In our actual world, the darkness of night allows us to see distant stars and the band of the Milky Way. In a binary system, true darkness would be much rarer, occurring only when both suns had set and neither was illuminating the atmosphere from just below the horizon. The reduced frequency of dark nights would significantly impact astronomical observation, potentially affecting how any intelligent species would develop their understanding of the cosmos. The length of these various illumination phases would depend on several factors: Earth's rotation rate, its axial tilt, its position in orbit around the primary sun, and the position of the second sun in its longer orbit. These factors would interact to create complex patterns that varied not just seasonally but over decades and centuries. Earth's rotation itself might be affected by the gravitational influences in this system. Tidal interactions with two stars could gradually alter our planet's rotation rate over geological time, potentially resulting in longer or shorter days than the 24-hour cycle we know. For any observers on this hypothetical Earth, the calendar would need to track multiple cycles: Earth's rotation, days, its orbit around the primary sun, years, the position of the second sun, and perhaps the alignment of the three bodies. Rather than the relatively simple lunar and solar calendars of human history, timekeeping would need to account for much more complex astronomical relationships. Religious and cultural practices would certainly evolve around these cycles. Just as many Earth cultures developed solstice and equinox celebrations, inhabitants of a two-sun world might mark special occasions when the stars achieved particular alignments, perhaps celebrating the rare periods of complete darkness as moments of particular significance. The weather patterns on a two-sun Earth would be characterized by one defining feature: extremes. The additional energy input from a second star would intensify Earth's atmospheric circulation, creating weather systems more powerful and unpredictable than anything in our planet's actual history. The fundamental driver of Earth's weather, the uneven heating of our planet's surface, would become even more pronounced. When both stars illuminated the same hemisphere, temperature gradients between that region and the cooler parts of the planet would steepen dramatically. These enhanced temperature differentials would generate stronger winds as the atmosphere worked to redistribute heat. In our single-sun world, the Hadley, Ferrel, and polar atmospheric circulation cells create relatively predictable global wind patterns. In a binary system, these circulation patterns would distort and shift as the second sun moved through its orbit. Trade winds, jet streams, and monsoon cycles would follow new, more variable paths, creating weather patterns that might seem erratic to observers. Storm systems would likely become more energetic, fed by the additional heat energy in the atmosphere. And oceans. Hurricanes and typhoons might form more frequently, reach higher intensities, and follow less predictable tracks. Thunderstorms would potentially grow more violent, with increased lightning activity and precipitation rates. The planet's hydrological cycle would accelerate significantly. Higher evaporation rates from the warmer oceans would increase atmospheric water vapor content. This would not only contribute to the greenhouse effect, further warming the planet, but would also provide more moisture for precipitation events. Some regions might experience rainfall of unprecedented intensity. Conversely, other areas could face severe drought conditions. The reorganization of atmospheric circulation would likely create new desert regions where sinking air masses consistently prevented cloud formation. These arid zones might shift location over the centuries-long cycle of the second sun's orbit, forcing ecosystems to adapt or perish. Temperature extremes would pose particular challenges for life. During alignments where both stars heated the same hemisphere, surface temperatures could soar well beyond anything experienced in Earth's actual climate history. Heat waves lasting weeks or months might become commonplace during certain orbital configurations. The oceans, which serve as Earth's thermal regulator by absorbing and distributing heat, would face increasing acidification and stratification in a two-sun scenario. Warmer surface waters would mix less readily with cooler deep waters, potentially disrupting nutrient cycles crucial for marine ecosystems. Ocean circulation patterns like the Gulf Stream might significantly alter their paths or strengths as temperature and salinity gradients changed. One of the most dramatic impacts might be on Earth's cryosphere, the frozen portions of our planet's water system. The periodic intense warming caused by the second sun's closest approaches could potentially prevent the formation of permanent ice caps, even at the poles. Without these reflective surfaces bouncing sunlight back to space, Earth would absorb even more solar radiation, creating a positive feedback loop of warming. Sea levels would fluctuate dramatically over the centuries-long orbital cycle of the second sun. During warmer periods, thermal expansion of seawater combined with meltwater from ice sheets would raise ocean levels, potentially inundating coastal areas. During cooler phases, sea levels would fall again as water became locked in reforming ice sheets. To remain habitable under these conditions, Earth would need robustly effective feedback mechanisms to maintain climate stability. The carbon cycle, the exchange of carbon between the atmosphere, oceans, biosphere, and lithosphere, would need to operate more efficiently to compensate for the varying energy inputs from the two suns. Weathering of silicate rocks, which removes carbon dioxide from the atmosphere over geological timescales, might accelerate during warmer periods, providing a negative feedback to limit temperature increases. Similarly, biological productivity might increase under favorable conditions, sequestering more carbon in organic matter. Despite these challenges, pockets of habitability would likely persist even during the most extreme phases of the binary cycle. Deep ocean environments, protected from temperature extremes by their thermal inertia, might serve as refugia for marine life. Highland regions could provide cooler conditions during hot epochs, while geothermal areas might offer warmth during cooler periods. If Earth had formed in a binary star system, the trajectory of life's evolution would have followed a dramatically different path. The variable conditions, from climate oscillations to complex day-night cycles, would have selected for organisms with exceptional adaptability, potentially accelerating the evolution of certain traits while hindering others. The most successful species would likely be generalists, organisms capable of thriving across a wide range of environmental conditions. Specialists adapted to narrow ecological niches would face greater extinction risks during the dramatic transitions caused by the second sun's orbital cycle. This selective pressure might have profound implications for biodiversity patterns, favoring fewer, more adaptable species rather than the rich specialization we observe in Earth's actual ecosystems. Intelligence itself might have evolved earlier, or in different lineages under these conditions. The ability to predict environmental changes, remember past cycles, and prepare accordingly would confer significant survival advantages. Perhaps on a two-sun Earth, multiple intelligent species might have emerged independently, each developing technologies to cope with the unique challenges of their world. From a cosmic perspective, our exploration of this hypothetical scenario offers valuable insights into the habitability of planets in binary star systems throughout the galaxy. Approximately 50% of Sun-like stars exist in binary or multiple star systems, meaning that a significant fraction of potential exoplanets orbit not one star, but two or more. NASA's Transiting Exoplanet Survey Satellite, TESS, and the James Webb Space Telescope, JWST, are currently expanding our understanding of planets in binary systems. Several circumbinary planets, worlds that orbit both stars in a binary pair, have already been discovered, including Kepler-16b, nicknamed Tatooine, after the fictional two-sun planet in Star Wars. Most of the binary system planets discovered thus far are gas giants unlikely to harbor Earth-like life. However, the detection capabilities of our instruments bias us toward finding larger planets. Smaller, rocky worlds may well exist in these systems, but remain below our current detection thresholds. The question of habitability in binary star systems has profound implications for our search for extraterrestrial life. If stable conditions for life can persist despite the complexities introduced by a second star, the potential habitable zones in our galaxy expand considerably. Conversely, if the challenges prove too great for complex life to develop, we might need to focus our search more narrowly on single-star systems like our own. Recent climate modeling by researchers at the University of California, Riverside, and other institutions suggests that planets in binary systems could maintain habitable conditions under certain circumstances. The key factors appear to be the separation between the stars and the specific orbit of the planet. Wide binaries where the stars remain distant from each other offer the most promising scenarios. As we continue to explore exoplanets, understanding the full range of possible astronomical configurations becomes increasingly important. If Earth had evolved with two suns, The beings looking out at the cosmos would have had a fundamentally different perspective on astronomy and their place in the universe. Their early scientific development would have grappled with more complex celestial mechanics from the outset. The regular patterns of a binary star system might have provided earlier insights into gravitational relationships and orbital dynamics, potentially accelerating their understanding of physics and mathematics. From a philosophical standpoint, life emerging under two suns might develop different conceptions of duality, cycles, and cosmic order. Their mythologies and religions would likely incorporate the dynamic relationship between their two celestial parents, perhaps viewing the interaction between the stars as a fundamental principle underlying all natural phenomena. As we continue to discover and characterize exoplanets, scenarios once confined to science fiction become subjects for serious scientific inquiry. The question, what if Earth had two suns, is more than a thought experiment. It's a window into understanding the true diversity of worlds that may exist among the hundreds of billions of stars in our galaxy. By exploring these alternative astronomical arrangements, we gain perspective on our own planet's history. Earth's relatively stable conditions under a single, well-behaved star have permitted the gradual evolution of complex life over billions of years. The relatively narrow range of climate variations we experience has allowed specialized adaptations to flourish, creating the rich biodiversity we see today. Yet in other star systems, life may have followed very different evolutionary paths, adapting to conditions we can barely imagine. As we look toward the stars and wonder about other worlds, we might find that the strangest aliens aren't those with different biochemistry or physiology, but those evolved under different suns altogether, life forms shaped by cosmic rhythms, unlike anything in Earth's long history.